coming. My name is Raj Hazra. I am the General Manager for the Technical Computing Group at Intel. And as Joe promised, I'll talk a little bit about what that is. And then for the rest of my time, I'm going to tell you a lot more about what we're doing in supercomputing and high-performance computing, and hopefully you will find that both informative and entertaining.
That's the entertaining part.
That's the cruise part. So technical computing, while we're at this show, at this event, it's about either you hear the word supercomputing, and of course high-performance computing is a word that's been used for decades now. So what is technical computing? And what is this group that I lead? Technical computing is, in our world at Intel, and hopefully in a broader sense, a very aspirational goal, which revolves around the use of computing, not just in supercomputers or in HPC, the use of computing to create an intellectual property. We all know that as information is becoming one of the most valuable equity elements in our economy, computing that creates more of that valuable equity, which is human intellectual property, through creation, design, and simulation. So this is all about, technical computing is all about turning data, and every passing day we see the opportunity for more data, turning that data into information, which there's gobs of out there today, but fundamentally then into knowledge. Knowledge is what this world has defined as its unifying economic currency. It's intellectual currency, and that's what technical computing is all about, is to serve, increase the value of, and increase the amount of that currency in the world. The part that we are really excited about in technical computing is doing that, creating the underlying fabric and those capabilities for computing, with the notion that customers demand that capability and the capacity to get the results quickly and get the right results. As fundamental as this transformation of data to information to knowledge becomes to the fabric of our lives around the world, it is very important that that fabric be reliable, be strong, and be able to extend and cover all the uses that we even don't foresee today. And so that's why it's about creating this currency. Technical computing then is computing which serves an intellectual property design through creation, simulation, or analysis, and the commitment to get that results in due time and to get the results right. That is hugely aspirational and inspirational for us at Intel, because we see that as serving our corporate mission of touching and enriching every life on the planet today and in the future. Right? So for us, from an Intel perspective, our corporate mission is about touching and enriching every human being's life, independent of geography, independent of walk of life, independent of age, where you are in your life. That is to touch everybody today and in the future. Technical computing, through the property of being the creation of the basic fundamental equity currency of that life going forward, is at the center of what we do as part of our mission, as part of our commitment to the world. And it's an honor to be able to lead this effort at Intel, along with a very fine team both inside Intel and a great set of partners, friends, and collaborators outside Intel. I talked a little bit about the fabric of our lives and how virtually in every space you will spot technical computing. Pretty much like 30 some years ago, Gordon Moore, when he came up with Moore's Law, walked around his house one day and did this mental exercise of looking at everything and saying, how many things could actually use a microprocessor? If you do that in the world today and you look at what people are doing and try to do that same exercise Gordon did with trying to spot the elements of technical computing, you see it everywhere. You see it in the fields of science, you see it in the field of economics and running our financial systems. You see it in spades in many other walks of life, such as research, such as healthcare, such as creation of things, such as, I could go on and on and on. The point is that universe of usage creates a continuum of solutions. Some that are done effectively and efficiently on something as compact and un-HPC-like looking, like a workstation or a client. Two, the traditional servers, and then of course the very large-scale supercomputers. While these may look discontinuous due to their form factors and how they are used, because they participate in this continuum of usage, in this continuum of capability of creating intellectual property, where you need it, when you need it, and creating it correctly, we look at workstation servers, supercomputers, and then delivered through the cloud some of these capabilities as essentially the fabric of the continuum of solutions. So our focus is actually being derived from technical computing isn't just about supercomputers, isn't just about workstations, but it's creating that continuum in the technical computing space that stitches these together to create workflows and usages that help enhance that creation of the fundamental knowledge economy currency. So in my group, we have work going on in very large-scale systems, down to what we would do with individual clients. We have work going on in how do we develop these capabilities with a mind to how they will be deployed through interesting mechanisms like the cloud. An example of such, the continuum of solutions and continued interest and investment is, I thought it would be timely this week, if you've all seen the top 500 list, is to look at the cluster at Purdue University. It's a publicly funded, driven by the university and its commitment to research and engineering. It's particularly an honor for Intel because it's actually named after Dennis Carter. And many of you that don't know Dennis will actually have seen what Dennis has done every time you see Intel Inside. He was the creator of Intel Inside, right? This is a wonderful example, yet another example of the continuum of solutions and people finding technical computing to advance what they are, what their mission is, and what their needs are, which is science, research, purposes. So, as I said, from our perspective, we've done this. We used to have the high-performance computing group, we used to have the workstations group, and we used to have various elements of technical computing. None of them are new to Intel, but we had them organized differently. We brought them under this aspirational and logical banner into one group, which now has the spectrum of platforms, from workstations to supercomputers, and some of the most important products that feed that capability, such as the Intel Many Integrated Core products that I'll talk about in a second. For us, from a business perspective, it's about 1/3 Intel's data center business and growing rapidly. It is driving, in many ways, our investments and our direction in where we take these capabilities forward. So a very key part of both our commitment, our mission, and our business objectives for the future. We stand at a pivotal moment in the virtuous cycle of a universe of opportunity. That's what the foil title says, and I read it out perfectly. But what it says below is even more profound. Many have questioned in the last few years, especially with the economic climate that we've lived in, whether the virtuous cycle was going to slow down or more so completely evaporate. Some have not questioned it from the economic perspective, have simply said, is there need for more? I remember as very early on in my Intel days, being faced with the question that came out in PC Magazine, is 300 megahertz good enough? And there were entire articles written around 300 megahertz and 640 kilobytes of memory. Many of you probably will remember some of those days. Well, a similar thing has happened in the technical computing space, if not more so in spades, as they say. The world is just about tasting the benefits of petascale computing today. If you go look at the top 500 and you draw it from 1 petaflop to 1 exaflop, the fastest system sits just about at the beginning of that curve. But the world is already looking to exascale as the next frontier. Why? Not because petascale is becoming boring to write and exa sounds more interesting. It's because of the perceived benefits of continuing to scale the capability going forward, accelerating some of the great work that can be done in support of various missions, whether it's science, whether it's engineering, whether it's national security. And that is driving, in turn, and being driven by, in some sense, some of the great technological advances that are continuing to work as 3 elements of a gear system to keep this moving forward. So technical computing is not at doldrums. Technical computing is poised to take off for its next destination, driven by interest, driven by need, and driven by people's innovations that allow that dream to come true. We are proud to be a part of that. It's our commitment to continue to be a part of that, and hopefully some of the things I tell you for the rest of this afternoon will convince you that that is indeed true. State of technical computing, as I said, as an amplification to what I just said, is not slowing down, right? Many of us live in our worlds today where we look at the macroscopic picture through microscopic events. A bad planned decision for someone. You didn't get your allocation of funds. Your system got pushed out to next year. You weren't able to hire a certain number of people. You can look at all of those things, add up those microscopic elements, and start to paint a real bleak picture. However, if you step back and look at what is really going on, the picture is slightly different, or much more positive. I'm showing you some elements of examples of some significant investments that are being made now in order to advance the state of the art and the availability of these kinds of capabilities to the mission benefits of technical computing. Tax stampede system will be more than $50 million over 4 years. For many of us that do Washington, D.C. runs very often, I believe the term is called, that's not chump change, right? The TriLab Linux capacity cluster, again, you'd be familiar with this, is a multi-million, multi-year contract. The interesting things are, it's not just the number of zeros in the award, but the fact that there's a commitment to take it forward for multiple years. And it's not just a US phenomenon. If you actually do the math on the top 500 list over the last few years and watch trends, supercomputing has really gone global. And in fact, the rise of Asia, and in particularly China, in providing more and more of this capability at a faster and faster rate of introduction is quite stunning. China, Russia, and many other countries soon to follow have all announced their exascale initiatives or high-performance supercomputing initiatives. Ask yourself, the global economy, this is not just a US issue or a Europe issue or a Greece issue. We are stitched together in a global economy. Even in the somewhat pessimistic views of such an economic picture for the next 5 years from which no one is immune, this is the kind of commitment based on a conviction of the importance of technical computing that the world is putting down. And we think that is absolutely elements of leadership and foresight. Coming back to the nearer term, the November 2011 top 500 list. The Xeon processor 5600 is the #1 processor generation on list with 223 systems. The Xeon processor E5 family, the E5 family is 10 spots on the list, including number 15, the Lawrence Livermore system that we've talked about. This is within a month or two of introduction of actually making these chips available. That's how fast the adoption is, and this is only tip of the iceberg. There are systems publicly announced, such as the systems from Jansi, LRZ, IFARC, that have been publicly announced with this processor family that are not yet. They were not ready for the top 500 list yet. They exist in the world, and they are providing these capabilities to their users. 85% of the new systems on the top 500 list run on Intel. More importantly, those such as countries such as China that have had a tremendous rate of adoption of high performance computing, 93% of the new systems introduced in China run on Intel architecture. We have 5 systems in the top 10. It was an interesting phenomenon this year, I guess, for many of you that have tracked this, not to have the top 10 change fundamentally in positions. But this is a reflection of the continuing force and the benefit of the technology that we bring to this marketplace. And we are very happy to see, not us talking about how good it is, but our customers talk about it by voting with their systems and essentially their wallets. And in particular, we are very, very proud with the newest member in our Xeon family, the Xeon E5 family, with a max 152 gigaflops per socket, with a 91% efficiency. 172 peak gigaflops per socket, which represents a 2x improvement relative to our previous generation, with a combination of innovations like AVX or advanced vector extensions technology. If you look at the right-hand side, these are published numbers, and you can compute them from top 500. The blue is the Xeon E5 family. The green is AMD's recently introduced Interlagos processor, right? If you look at the bars on the right first, the peak gigaflops reflect a significant advantage for E5, and coupled with the higher efficiency that we achieve through our microarchitecture and other innovations, the effective gigaflops difference is actually significantly higher. Why do we worry about effective gigaflops? Because peak is an interesting but somewhat rather trivial mathematical exercise of multiplying a few numbers. Effective is what people see, is what applications see, and it's what users of these systems see as the return on investment into these kinds of systems. So we are very proud of the performance leadership that we have with this product. In many ways, and you are probably the first in the community and the world to hear this, the next set is just as important, if not more, in terms of the value and our pride. The Xeon E5 family is the industry's first integrated PCI Express Generation 3 capable processor. That is, it's our commitment to not just increase the performance, but increase in terms the total capability with matching advances in the I/O subsystem that make these scaled systems using these processors so much more effective. That you can hope to see not just node efficiency go up, but scaled system efficiency go up as well, given the advances in the I/O subsystem through integrated PCI Gen 3. With 2x the bandwidth. For the high performance community, that is always the trailblazer for new technologies, But more importantly, it's not just for kids, because it benefits from state-of-the-art, latest generation technology. PCI Gen 3 is a must-have for scale system performance. And using anything else just does not seem to make sense, or it seems to be going backwards. So we are very excited with this capability. As you saw on the show floor, the rest of the ecosystem has embraced this capability and the benefits very aggressively, and you will see more of that to come in the future. In particular, if you look at, if you've seen the Mellanox booth, with their advances to getting to full data rate or FDR InfiniBand on PCI Gen 3, that is an example of a leading edge advance in the I/O and systems capability above and beyond node performance or computational performance in systems, and we hope and expect to see many more of this. But the Xeon E5 processor family, with the stunning performance improvements over previous generation and the integrated PCI Express Gen 3, becomes essentially, across all those factors of how you would evaluate, the foundation for high performance computing for this year and beyond. Using anything else would be making compromises. That's the way we feel. That's the way our customers are telling us they feel by how they're adopting this technology. If you look at application performance that we can achieve, or we are achieving and our customers are achieving with the E5 family, and on this chart, the baseline is the Xeon 5690. As we look at a benchmark, a synthetic benchmark like matrix multiplication, that's a critical component of LINPACK, we are at about 2.1 relative to the Xeon 5690. You can say, well, that's great, but that's one of many different mathematical operations. How does this affect real applications? That's the set of blue bars on the right. From life sciences to computer-aided engineering to energy to financial services and other large-scale applications like numerical weather simulation, we are seeing anywhere from 1.3 to 1.7x performance improvement in the same power envelope across all of these categories with the use of the Xeon E5 family of processors. This is a stunning improvement generation to generation, and fundamentally driven by several things we have done in the microarchitecture with the addition of AVX and the process technology advantage and capabilities we have through a relentless pursuit of Moore's Law. Okay? How many of you think this is impressive?
But it's a non-launch product. That's a problem.
Okay, we'll talk about that here in a second. Okay. Now I've stood up here and talked a lot about what the E5 is, what the E5 could do, its potential. Nothing is as satisfying or credible as hearing someone who's actually bought this and has put this in practice, and why this is as good or better than what I said it was going to be for their purpose. So I'm very pleased to invite up Alain Lichnevsky, the Chief Strategy Officer? Scientific Officer of Jansi, one of the leaders in Europe on deploying high-performance computing for various spectrum of of technical computing application, and I'll let him speak to it. Thanks, Alain.
Thanks for the invitation. I hope the mic works. So I'll give you some explanation on the new system we are putting into service. I just have to press this. I can even do that, so it's good. Okay, so I'll give you some context. So Jansi is the entity which has been set up to fund, acquire, and have our national scientific supercomputer exploited in several computer centers for academic research, but also for industrial research in some respects. So Gen C has three major strategic priorities. The first one being to fund and acquire the systems. And then Gen C is contributing to the organization of a European HPC ecosystem, of which you've probably heard of the PRACE infrastructure, which is putting now in service several very large machines. Curie, which I will be describing, is the second. There are 2 machines in Germany at the moment, and this number will increase, and we're expecting supercomputers in Italy and Spain. And of course, doing that, it is also our responsibility to promote the use of simulation and high-performance computing in both academic fundamental research and also industry for all the good purposes that the country is expecting. Since Gen C has been started, which is 4.5 years, we've been able to deploy a number of machines, and we have been increased by a factor of 30 the available bulk computing power in France, and this has been matched by the fact that our user community has grown and has even more applications, and is looking even into more ambitious applications, either by our own growth or by the European and international corporations. And in doing this, we have been using several manufacturers, several architectures, and we have to do that in order first to deal with a large number of application domains which have different views or requirements, and also using competition for getting the best equipment in use. So the European context, PRACE research infrastructure has been operating since April 2010. It was preceded by a preparatory phase funded by the European Commission. Technically, it's set up as a legal entity in Belgium, and France is represented into this by Gen C, so we have a significant strategic goal into seeing PRACE succeed and bring all these benefits. We are providing Tier 0, that's data scale service to the scientific and industrial community since August 2010. And as I said, we will open more machines next year. The total funding secured from the major hosting member states, which are France, Germany, Spain, and Italy, is 400 million euros over the period of 5 years for which we do the accounting. Then there will be the next period for which I cannot talk. We also got 70+ million from the European Commission because of the importance of the goals and the importance of getting all European countries involved, because of the importance of the IPR that we expect to develop, and also the creativity and the scientific results we expect. So now if we turn to the machines we are currently putting together, which we have bought, and it's called Curie, and it's the machine that will support the French commitment to PRACE. So basically, you know the total cost of operation and funding we have put into this. It will reach 2 petaflop overall capacity by the end of this year. We are currently in the process of installing, and a large part of the machine is already operating. There's a large attached storage, because many of our application domains, either in biology or climatology, use very large data sets and produce lots of simulation data. This machine is a very large parallel machine with more than 92,000 cores. I won't get into the technical details. I have more on next slides. And it's operated and installed at TGCC, which is a large computer center operated by CEA, one of the research agencies in France. Now we can give you more technical information, which will show how we are able to get this very large performance, of which we are very happy. And we'll also make the link with the talks of the previous and next speakers. So basically, we have a machine which is partitioned in 3 partitions. The last one here, which is called a scene node, is a 1.7 peak petaflop. It's obtained using Xeon E5 processors, large memory, and 80 plus 1,000 cores. So it's very parallel. We also have a flat node partition, which has been open for a year now, which is used for many workloads, and also in our overall workload once the whole machine is operating. This has several advantages, so we can speed the workload and use the machine even more effectively. All of these partitions have been using Intel processors. They've been integrated by Bull and delivered to us, or for the last part, currently being installed. We also have an hybrid node partition, which is important because we need to be able to prepare application for the future, whatever the future will be. One of the possible ways to do it. There are apparently others, but we are putting our investment in such a way that our codes are ready for the next challenges. Of course, we do this as a tool to bring service to science and open innovation, which is the creation of IPR in a very competitive world. On the Xeon E5 partition currently being installed, we have been already able to run a large part of it. And we have very good performance. Already noticed that the level of memory controller, cache management, this gives improvement in stream performance, which we found is very important for our workload. We are quite happy with, or very happy with the power management and the file system implementation. We are also very happy with the compilers and the libraries for the new AVX generation that comes with the E5. So it's very important for us that things are mature and usable when we introduce, because our users want to get on the machines quickly. It's good to have new innovative technology, but the faster we can get it into production, the better for us. Technology evolves, as you know, very quickly. We've seen all these curves. So we are really very eager to get things going quickly. Plus, we have a lot of scientific challenges to address. The users are already lined up with computer time attributed for the next half year or next year. So people have very high expectations. Before we do that, we'll have the ability to run a number of grand challenges on the whole machine. This is done, of course, for the importance of the results. It is also done in such a way that we have the whole machine under control, being used so that we can thoroughly test the equipment before we open it for general usage. So general usage through Prace for Curie will start on March 1st next year. And as I said, the users are already lined up, so there are large expectations. Our applications domains are very large. I mean, you're seeing engineering application in the would say, the power plant for aircraft. We have a number of things in climatology, which is of interest, chemistry, energy, and astrophysics, which is maybe more remote, but also very interesting as a way to understand the universe. Especially these days, that neutrinos are really going very fast, so we have to we have to keep up to that, or apply some, I would say, yeah, critical sense. Another example, which is ready, has been used on a smaller partition of Curie already, and will be used on a large machine. The Grand Challenge period is, the example is linked to the chemistry of the Alzheimer's disease, and using quantum Monte Carlo chemical code, we have been able to get interesting results explaining some of the phenomena and mechanism, and we will extend this simulation to get a better understanding yet of these phenomena. It is important, this code has also been largely optimized by the lab that Agency, Intel, and CEA are running in France, and which is bringing a lot of, I would say, expertise to making the best use of our machines, to code tuning, and also to preparing code for next generation. As you see, there are two challenges. One of them is, since we allocate an entire machine or a large part of the machine, we have to go to extreme level of parallelism. So it's already difficult to make several people do things in a nice synchronized way, but here we have to have, I would say, 100,000 processors, which are what they are, do things in a fully organized way and fully cooperating way. So that means the software challenge is high, and we also want to fully exploit their characteristics. So we have experts, but the French lab, ECA with Intel and CA, is also a way to improve this and be able to prepare quickly for the next generation, both of code and processors, which is a thing which we are very excited. It helps us think place quickly. So, thank you.
Thank you.
Says it's always gratifying to see real science being done on the technologies we create, and particularly in references to users being lined up to use this new capability. That's exactly what we're looking for. Not only because it's validation of the work we've done, but it also helps us continue the treadmill and continue the innovation process with feedback from our customers and those that are using these machines to get real work done. Talking about innovation, the cycle continuing, what's next? Let's spend a little bit of time this afternoon on that. We've talked a lot about the Xeon processor family in many ways for several years, and continues to be now. It's the foundation of HPC performance. It is suited for a broad scope of workloads. You know, Alain talked about workloads with compute, memory, doing different levels of balance. It's proven itself as a very capable general purpose performance, power, and cost-effective solution. Industry-leading performance per watt for serial and highly parallel workloads. In ISC, we had announced last year that we were embarking on the journey for what would be another complementary and potentially in the future the path to continue architectural innovation forward. And we announced the many integrated core, aka MIC architecture. That's the picture on the bottom. Essentially, the MIC architecture is not just Xeon architecture on a bigger die, because that is not technically or economically possible. But it is a new architectural approach to look at high levels of parallelism as the way to deliver performance for those applications and workloads that are highly parallel. And be able to do it in a way that delivers the greatest performance per watt and efficiency, but perhaps more importantly, with the highest level of productivity. So, our goal is, and our vision is, that as the Xeon processor family continues to do the work, and as new work emerges in the highly parallel area, that we find a way and we introduce and provide a way to actually harness that parallelism in products and architectures and products we provide, but do so in a way that the paradigm in which people, customers, software developers look at these multiple architectures is simplified through a unified programming model. One of the learnings that we've had and generated over the last 30-some years of being in the business is that a new technology, when introduced, is great, but you have to keep in mind barriers to adoption. For an ecosystem, for a user base that's as large as it is today. And destroying that without a very, very good reason is often very expensive, if not fatal. So, as we proceed down this path of maturing the Xeon architecture, adding innovations to it like AVX, and as we introduce and ramp the many integrated core architecture, we are seeing very, very good acceptance of this philosophy and eagerness to embrace this path forward. The Texas Advanced Computing Center, which today has a data center, it was recently operationalized. It has targeting codes in biology, astrophysics, CFD, and other areas of science, has announced publicly that a new cluster called Stampede, which is a 10 petaflop new machine. Now, 10 petaflop new machines, you can say, okay, we expect that sometime next year, right? I mean, with the rate of progression of the top 100. The most notable thing is it's a 10 petaflop machine with Xeons and at some point many integrated core in it, right? So it's a commitment to take forward the philosophy that we put forward in which Xeon and the many integrated core architecture work together to create a continuum of increasing capabilities. Very, very pleased to work with TAC on this. As we ramp the many integrated core architecture and we look at some of the interesting technical aspects of maturing and advancing this technology, we're also very pleased to participate and collaborate with architectural experts such as Sandia National Laboratories. We have in operational in 2011 what we would call a test cluster of Xeon and Knights Ferries, which were our software development platform for the many integrated core architecture line. Not a product, but a software development platform that gives programmers the ability to look at the value of this architecture, tune their codes, but more importantly, do research, start doing research in what such a future entails from a system software and programmability standpoint. That is what the work we are doing in collaboration with Sandia National Laboratories as an interesting path forward and a commitment to seeing this path forward through the era of multi-domain core. Very, very exciting. The one that I have to mention with a smile on my face is the work we've kicked off and done with Oak Ridge National Laboratories. Oak Ridge needs no introduction to anybody in the high-performance computing space as a leader in high-performance computing and the role they've played in not only advancing high-performance computing, but providing that capability for science and other mission uses over the years. One of the things that I would like to do is not talk about Oak Ridge myself, but ask Dr. Jeff Nichols, who's the acting director and associate director and deputy director, all the adjectives you can put before director, of the Computing and Computational Sciences Laboratory, the heart and soul of where Oak Ridge drives some of these advances in high-performance computing technology and applications from. I would like Jeff to come up and tell us what he's doing at Oak Ridge and with us.
Great, thanks, Raj. So, as Raj mentioned, I'm the Associate Laboratory Director at Oak Ridge National Laboratory. Oak Ridge National Laboratory is the Department of Energy's largest multi-program Office of Science laboratory. And we're really well known for three things, okay? And unlike Rick Perry, I will remember all three. The first is, as Raj said, is in computing and computational sciences. The second is in neutron sciences and materials. And the third is in nuclear energy. And we're all about delivering science, okay? So at Oak Ridge, as you know, being around supercomputing for the last 20 years or so, you know about Oak Ridge National Laboratory. All right, we host 3 national centers in computing. We have the Department of Energy's largest computer in Jaguar, which is hosted at the National Center for Computational Sciences. We have the National Science Foundation's largest computer, Kraken, which is hosted in the National Institute for Computational Sciences. And then we have the NOAA, the National Oceanographic and Aeronautical Administration's largest computer, named Gaia, okay? And it's in the National Climate Change Research Center, all of those at Oak Ridge National Laboratory. So you know us because of the hardware that we actually put on the floor, but hardware is hardly exciting. It's exciting for our vendor partners, but it's hardly exciting. The exciting part is doing the science, okay? And we talk about science at Oak Ridge, and we talk about doing science on these large machines, and we also talk about doing the science in conjunction with the other kinds of instruments that we have at the laboratory. So it's an instrument of use to us to enable us to do the science that we do, the science objectives. The key here is scalable, okay, scalable, scalable, scalable. You got to have scalable computing and computational sciences. You got to have scalable data and data analytics, and you got to have scalable infrastructure, right? You have to have that 25 megawatts of power and 600 tons of cooling and 100 gigabit networks. All of that is important, as well as the scalability of the hardware and the software, okay? But the key is to deliver leading edge science relevant missions. I do this, okay? Partnerships is also extremely important. And there's a vast array of partnerships that is required to maintain leadership in computing. Okay, you can't do it by yourself. We've got to have the relationships that we've had with Intel over the years. We have a memorandum of understanding with Intel to go forward in doing the kinds of science objectives that we have at Oak Ridge National Laboratory. So we have to have international, interagency, multi-institutional, multidisciplinary, all the buzzwords that you know is required to do the heavy lifting in order to be able to accomplish the science. And that's very important. Raj?
Yeah, sure.
Plug in or find another power source.
Keep going.
Okay? Well, it won't be hands. Okay, I can do that. Okay, so when we talk about scalability, we've talked about hardware, software, we've talked about the systems, we've talked about the infrastructure. It's very important to realize that when we talk about scalability with regards to computing and data, we have to have scalability across all of these domains, applications, algorithms and analytics, tools and middleware, et cetera, et cetera, et cetera. Scalability, we have Jaguar, for example, today has 230,000 core processors, 230,000 concurrency or threads that we have to worry about with regards to scalability. The machine, we are upgrading Jaguar now, and it will have millions, if not 10 million, threads of concurrency to worry about. And so it's very difficult for us to think about making those applications scale But today, we already have a half a dozen applications that sustain a petaflop or more of performance. And these are not toy applications like LINPACK. These are applications in chemistry and material sciences and nanosciences and all across the board, superconductivity. So we already have sustained petaflops, and we want to go to sustained exaflops. And in order to do that, we have to figure out how to do the kinds of parallelism with these millions, if not 10 million or a billion threads of concurrency. Okay? So we've already been working for many, many months on how to program Jaguar when we upgrade that machine to 10 million ways of concurrency. And it's very, very hard. But I can tell you that the thing that excites us about Intel and this mic chip is how it exposes that parallelism and how it gives us the application performance that we desire. Okay? And so that's what's really important about our relationship with Intel and what the mic chip brings. And so we have already been using the mic chip at Oak Ridge National Laboratory. And so we're going to talk to you a little bit about our experiences with regards to that, that particular chip. And the person that's going to do it is the guy that actually is the scientist, the corporate fellow at Oak Ridge National Laboratory, Robert Harrison, who is one of our joint faculty members at Oak Ridge and the University of Tennessee. And he's the director of that National Institute of Computational Sciences that we host at Oak Ridge National Laboratory. He has already been exposing the parallelism in several of those applications that we've talked about. And he's already ported tens of millions of lines of code to the mic chip. And we're excited to tell you about that. And Robert, come up and talk to us about what's going on there.
Hey Jeff, thanks very much. So yes, I'm director of both the Joint Institute of Computational Sciences that is now a 20-year-old institute that sits between Oak Ridge National Laboratory and the University of Tennessee. We're very proud to be home to the National Institute of Computational Sciences that is actually the National Science Foundation's currently largest supercomputer center. It delivers roughly 65% of all the cycles that NSF has. And this, in the next few days, we're actually very proud to be celebrating the delivery of our 2 billionth CPU hour. The path forward over this next decade, as we look at the rapid changing technology, as much as it's a challenge to the Department of Energy, in many ways it's a much larger challenge to the much more diverse and differently supported campus community and the myriad of research missions. And it presents also a challenge for people coming into the discipline, undergraduate and graduate students, new disciplines that want to be able to compute, but simply aren't able to get over that entry barrier of complexity. So one of the missions that we've taken upon ourselves is to play some leadership in that space. And the Application Acceleration Center of Excellence was established in part to this end, and also as a future technology program for NICS itself, so that we would understand and help contribute to the march of technology, emphasizing not just performance, but productivity. We too have established partnerships, and we're very proud to have a strategic relationship that's been established with a memorandum of understanding between ourselves, now the National Institute of Computational Sciences and Intel. And we've had multiple Knights Ferry cards, which is Intel's prototype or platform development kit to evaluate both the programming model and also to really work with Intel to help mature their software platform and also help drive the features that are present in it. Jeff mentioned the huge amount of source that we've managed to get going on this machine. And to be honest, we were absolutely shocked at the rate of progress. We came in expecting a much more raw software environment, more architectural and other challenges that we had to overcome. And in the end, we got off and running with just amazing momentum. So these large codes, NWCamp, 3 and a bit million lines of code, Enzo, many 100,000 lines of code, same goes for L. madness of several 100,000 lines of C++, and of course MPI, global arrays, a distributed shared memory programming model. Most of these had correct functioning ports in less than a day. And one of the key points that Raj made was it's not just the architectural compatibility down at the instruction level, but actually it's this preservation of a programming model that we understand in great detail after many decades of experience, actually going back primarily to the days of vector-gray computing, where we understood across large areas of science how to drive vector units, how to drive multi-threaded applications, and of course layered on top of that now is MPI parallel computing. Most of this software, I can confidently say, since I'm working on this myself, and the people here are working on this are the co-developers, will never run on GPUs as we understand them right now. In part because of just the sheer volume of software, millions of lines of code, and in large part because the algorithms, data structures, and so on associated with the applications, I just simply don't have the massive parallelism that is required at the fine grain to drive